L11 in our marathon of moments of inertia, the cone. Now the first one we're going to do is put the cone like this. And we're going to go along here, the z-axis, and we'll call this case 1. We'll say the central long axis. Since you could have a center going this way, we'll say the central long axis. The radius at the top, the largest, is going to be R, capital R, and the total mass, big N. And the height of the cone, H. Now the secret in doing this is to look at a disc. To look at a disc, and we know the answer for the disc. We have done that before. A disc is going to be 1/2 mr squared, where the mass of the disc is m and the radius is r. Now this here is going to have a little r, and this is going to be a height. If this is the z-axis, let's pick z equal to 0 to be at the bottom here, so that z gets you up to where this infinitesimal disk is. And this little thickness here, if we look at the thickness, is dz. Now we're going to need the volume of a cylinder, and often that's not memorized. It would be good for us to actually derive it using calculus, because when we do the moment of inertia, the integral is just a little bit more complicated, but it's very, very similar. So this will be good practice. So what we'll do here is look at the differential volume of this disk, which is equal to pi little r squared. That's the area of the disk. And then we need to multiply by the thickness, which is the dz. And then we want to integrate all these, add all of them, and we have 2 variables so far, the little r and the z. I would like to use z, since I already have the z there, as a dz. And to relate the two, we're going to draw a little triangle here, where this is a right angle, and this is z, to get you from the origin up to where the disk is, and this is little r. And before, when we did this with a sphere, we had this as some capital R, but here we don't have that case. So what we're going to do in this situation is use similar triangles. This triangle that I have drawn here, and compare it to the bigger triangle, which has the same angle, and it has a right angle. So all the angles are going to be in agreement, this angle here too. So we have similar triangles. So in that case, we draw the bigger one. The total height is h, and the radius at the top there is big R. And now we can set up a proportion where the little r divided by the big R is equal to z divided by h. So this gives us little r in terms of z as z over h times r, big R. So that's what we're going to use in our formula here for the r, little r. We're going to put that in there. So when we do that, dv is pi, little r squared means we're going to square z over h times big R. That's the little r here. And we'll have dz. So in this case, we're going to integrate the volume. To find the volume, we're going to integrate. And let's go ahead and put our constants out front. We have a pi out front. We have a big R squared over h squared comes out. And then we'll have the integration, and z is going to go from 0 up to h. And we have z squared, and that's the integral we need to do. Now this integral here is going to give us z cubed over 3 from 0 to h. The lower limit will give us 0, so we just put the upper limit in, h cubed over 3. And now we can give the result. The volume is equal to, there's a 1/3 here and a pi, and now this h cubed and h squared, there's going to be a cancellation. So let's write these down one by one. We have the 1/3, then we have the pi, and then we have the capital R squared, and then we have h cubed over h squared, which is going to give us h. And this is the volume of the cone. Often this top part is called the base, since you often see the cone. You often see the cone like this, where the bottom is the base. So you have here pi r squared gets you the area of the base, and then 1/3 times the height gets you your volume of the cone. So when we apply this to our moment of inertia due to the disk, we'll have an infinitesimal contribution of the disk. It's going to be 1/2 the mass of the disk times the radius of the disk squared. So the radius of the disk squared is r squared, and the mass is dm. Now the dm is going to be related to the volume by the density, rho dv. And we already know what dv is. See, we already have done practice. We have done this problem with the volume. So now we're ready to set things up, but we do want to know what that rho is. So let's first of all get the rho, which is the total mass divided by the volume of the cube, which is 1/3 pi r squared h. So dividing by 1/3 will bring the 3 in the numerator, 3m over pi big R squared h, and we want to save this for later use. We'll need that. So now we're ready to put in here for the dm, and then for the dv, we have this expression up there. So this will give us, for the di, we'll have 1/2, and we're going to have here a pi, at this point I would like to, for dv, go back to this form here just for now because it's simpler. So if we use this form for the dv up here, then I can write pi little r squared dz. Save the dz for later because this is an easy expression. Then when I put this in here, I have the 1/2, I have the pi, I have a rho, and I'll have r to the 4th power dz. So that gets me here very, very quickly. Now it's time for the r, and that's when I come up to here and bring that r into here. Well, actually, we want it there. We want it to the 4th power. So let's do that. So I have di is 1/2 pi rho, and the r is equal to z over h times big R, and that's going to be to the 4th power dz. All right. So this is going to give me 1/2, and we have here pi times rho, and then we have the constants, the r to the 4th over h to the 4th, and then z to the 4th, and then dz. So it's very similar to the volume integral we did, just a little more things are in the integrand because it's a moment of inertia. So if we do that and get the integration going, we'll have 1/2 pi times rho, and we have r to the 4th over h to the 4th, and then we have the integral from 0 to h, that's where z is going, z 4th dz. So this is going to give us z to the 5th power over 5 from 0 to h, which will simply be h to the 5th power over 5. So that means we have here the 1/2 and the 1/5 will give us 1/10. Then we'll have the pi and the rho. We'll put the rho first, rho pi. And then here we'll have r to the 4th. And then h to the 4th divided into h to the 5 will give us h, 1 power of h. Okay, so now we're ready for the density. And if we put the density in here, we'll have I is 1/10, that's this 1/10. Then comes the density, 3 big M over pi big R squared h, then pi, then r to the 4th, and then h. All right, now let's see what happens here. We have the pi cancels out. We have the h cancels out. And here r squared, when it goes into r to the 4th, will give us r squared. So the answer is 3/10 m r squared. And this has the dimensions of moment of inertia, a mass times a distance squared. And there is the moment of inertia for a cone about the central long axis. Now that one looks downright scary. So how do we do that one? Well, now we go to case 2. And this one looks very scary. This is going to be the axis. We're going to go here at the axis at the point where the cone goes off in a horizontal fashion like this. So axis at the point and the cone, say perpendicular. The central axis, the lengthwise axis of the cone is perpendicular to this axis. So we'll call this axis here X. And the secret will be to consider a little disc that's a distance X away. We want to sum these up. Notice that here we have a big R, and the diameter here is 2R. There is here a dx, a little thickness here, and h is the length of the cone. Now the way we're going to do this is we're going to think of, first of all, this as a coin being placed here, because then you have the spinning coin, which we already did. We know how to do the spinning coin. Then we're going to kick it out to here. In general, have it an infinitesimal disk, and then we're going to integrate from x going from 0 to h. So how do we relate the little r? See here, there's going to be a little r. And we do that by the similar triangles again, where here x and little r form a small triangle, and then there's the big triangle which comes out to here. X is going to be h, and the radius is maxed out with a capital R. So r, say divided by x, r divided by x, say this ratio here, is the same as big R divided by h. And this way, we can get R in terms of X. Now let me give the coin, say the coin, if it's at X equal to 0. We have the coin here, the same size here, at X equals 0. Remember that the coin that spins on its edge like that is given by 1/4 times the mass of the coin times the radius of the coin squared. So the mass will have the 1/4, and the mass is a dm, because it's going to be this mass element moved over to the origin for the moment. And that's going to be times r squared, because we're simply moving it to the origin. Then we're going to kick it. So the moment of inertia, when it's in place, as shown in the diagram, is going to be the 1/4 r squared, and then we're going to kick it out x. Now before we do that, let's just remind ourselves of the parallel axis theorem, that I is equal to the I center of the mass plus the mass times the distance we kick it from the center of mass, say axis. So here is the result of the center of mass, and we're going to kick it to the right. So this I, center of mass, is equal to the 1/4 dm r squared. And here, this is the dm. And then the d is going to be x, so x squared. So what we have here, when we do this kick, in fact, if you here this is going to be a differential, and this is going to be, say, di, the x equals 0 case, like that. So here what we're going to do is add all this up. The common factor here is a dm. So we have a 1/4 r squared plus the x squared, and we have the dm. All right, so we have here, just go ahead and write this out just to be sure that we have all the steps. We have 1/4 dm r squared plus the dm x squared. Okay, so then we come over here, we have the 1/4 of the r squared plus the x squared. The dm has been kicked out to the right. So now we're set. And remember, the dm is the rho times the volume element. Well, what's the volume element for the disk? Well, it's pi little r squared times your thickness dx. So this is pi little r squared dx. So putting all this together, we have di is 1/4 r squared plus x squared, and then rho pi r squared dx. Okay, then we come in with that r squared, we get 1/4 r to the 4th plus x squared r squared rho pi dx. And now we're ready to use the formula of what r is. Little r is big R over h times x. And I think maybe I could have factored this out a little better. Sometimes when you're doing problems, you change your mind as you go because there is an r squared in both places. But what we'll do here is we'll go ahead and do it the long way since we already started this. And we'll have the rho pi out over here at the far left. And then we'll have the 1/4. And then we go, the little r goes to the 4th power. So that's going to give us big R to the 4th over h to the 4th, and then x to the 4th. And then here we have the r squared with the x squared. So we're going to have an big R squared over h squared, and then x squared times x squared. So this will be x to the 4th dx. Okay, then what I would like to do here is do some factoring. Let's get out this r squared over h squared. So this big R squared over h squared, get that out of there. Then I'm going to have here, and also I would like to get the x to the 4th out of there. So kick the x to the 4th out to the right, kick this r squared, h squared out to the left. So this second term here is a 1. And then over here, x to the 4th went out, and a squared came out here. So this is going to be a 1/4, and you'll have a squared left because you had to the 4th power. So that's what you have. Let's just check that. Bring in the r squared, but the r squareds are to the 4th. H squared, h to the 4th. The 1/4 is there. bring the x to the fourth in from the right. There it is. And over here, what we have is, if we bring this back in, we would find it with the h to the fourth. So everything is fine. So now, for the integral, we have rho pi. Now look, all these are constants. Look at this. All this is constant. All this is constant. 1/4 big R squared over h squared plus 1. And the integration is this x to the fourth dx from 0 out to h. This gives us x to the fifth over 5 from 0 to h, which is h to the 5 over 5. And let's go ahead and get the rho in here. So I is 3 big M over pi big R squared times h. That's the rho, and then let's get the pi in there, here. And then we'll have a big R squared over h squared. And then we'll have 1/4 R squared over h squared plus 1. And what's the last thing that's tagging along here is the h to the fifth over 5. So let's see what cancels out here. Well, we're going to get a cancellation with the pi. We're going to get a cancellation with the r squared. Now here, we're going to have an h cubed term, and here we have an h to the fifth, and when we divide by the h cubed, we'll wind up with an h squared term. Now let's see if we can pull all this together. So I equals 3m. I'm just going to take my time, and I'm going to put the h cubed in here. I'm not going to cancel all the h's at the moment. And then this is then 3m. Pi's cancel, the r squareds cancel. I keep the h cubed for now. And then 1/4 big R squared over h squared plus 1. And then here, h to the 5 over 5. Okay, and now we'll have 3 big M, and here we'll have 1/4 R squared over h squared plus 1 times h squared, because now the h cubed divide in there, h to the fifth gets you the squared over 5. And we're almost finished. We're almost finished. Now I would prefer for this answer as actually to bring the h squared in. That's my preference here. So if I do that, I bring the h squared in, I'll have 3/5 m. I'll have 1/4 times r squared plus h squared. So I bring the 5 over here to the left, so it's 3m over 5. I then have the 1/4 r squared, and bring the h squared in, cancel that one, and then have it over here. Now my preference is to actually pull the 4 out to get this cool formula, and we'll do that over here, where we'll have I is 3 over 20. That is cool. Bring the 4 out. And then we'll have m, and then here we'll have r squared plus 4h squared. And let's check that. Okay, so let's check it. We have 3 over 5 times m. We bring out the 4. We have 3 over 20 times m, r squared. And then if you bring out that 4, we have to put a 4 in front of the h. So that looks good. And that is a very impressive result, because to do this from scratch would be very scary. Very, very scary. And here we have the result going around like that. Amazing.